we'll start at about 10 o'clock, yeah? Thank you for being here. Assalamualaikum, Dr. Asrul. You're muted.
Okay. Waalaikumsalam.
Okay, thank you.
Ya.
So we'll start at 10, yeah?
Can. Ya.
Okay, Assalamualaikum Dr. Asrul, apa khabar?
Waalaikumsalam. Ya, baik. Sihat, Prof?
Alhamdulillah. Work from home lagi ke USM?
Kita still work from home, tapi macam I punya kita buat schedule. Macam staff kita buat schedule lah, macam sidek stay on, tapi untuk staff admin kita buat schedule. Contoh macam minggu ni dia datang, minggu depan datang, so macam tu lah, macam per day at least ada 3 orang lah dekat center.
Okay, controllable lah ya.
Ya. Tapi tak tahu sem depan macam mana, how the UM still start face to face ke ataupun you still online?
Kami UM dah wajib minggu ketiga ni staff engineering ke campus.
Kelas for the October punya semester kelas macam mana? Kelas still
Kita panggil hybrid. Kita pun tak tahu apa hybrid tu apa.
Online and yang face to face tu mungkin akan dihybridkan bagi siapa yang ada di kampus dan siapa yang tak boleh balik, yang tak cukup dos kan belum tu. Tapi setakat ni lepas 2 minggu meeting faculty memang dia UM kata hybrid lah, jadi kami tunggu je lah hybrid punya facility ke apa-apa tu, kami tunggulah.
Hybrid. Your punya new SEM start bila?
18 Oktober.
Oh, maknanya kita orang extend to be 25th October lah, makna supaya so the last meeting like in USM, so we leave it to the school akan decide sama ada they are going to be online ataupun ada school yang akan be as a still face to face ataupun online lah. So tapi the second semester kemungkinan akan fully online lah, the whole faculty. The isunya bila buat fully face to face, isu dewan kuliah lah. I think the timetable punya coordination is quite
betul.
Kelang kabut lah.
Kelang kabut.
Memang kita pun tengok macam mana next month. Tengoklah macam mana.
Kami menunggu arahannya.
Kami buat
online especially insyaAllah lah kita dah janji dia online tu kita dah ready. Cuma bila hybrid tu kami pun first time nak mengalami hybrid punya platform kan, macam mana nak divideokan ke at the same time ada student yang depan kita kan. Jadi kalau facility tu done boleh nak make sure practical. So kami menunggulah pasal tu pun facility kan, ada facility kami boleh buat lah.
Yalah. Kita pun how the UM punya ni bila online ni dia susah kan, bukan susah dari segi evaluation tu kuat.
Memang very subjektif lah, tapi kita dah duduk dalam kena follow macam ni kan, kena adapt lah evaluation. Software yang baru pun kami dah ada software evaluation yang baru kan Dr. Sharifah di UM. Kita dah start diintroduce pada special software yang untuk buat evaluation lah, supaya tak ada isu-isu untuk meniru ke apa-apa kan. Kami pun barulah, belum lagi implement tapi dah mula training lah.
Okay. Saya my case lah, makna I ajar the last SEM Parma tau about 400 students. Sebabnya tu untuk khusus undergrad non-EE. So that mean for the all faculty akan ambil lah macam that courses. And then kan kita bagi assignments the first, and then kita dan ujung kita nak compile, and then I pun perasan ada kembar in my class.
Kembar lah banyak tu, triplet semua ada tu. Itulah, itu cabaran lah. Pihak universiti kena ambil orang kata ikutlah bajet macam mana kan. Bila kita kata software tu maksudnya bukan free Jadi kena tengoklah support bajet macam mana dia nak implement, kita pakai je bagi training, kita pakai lah.
Betul.
So okay, Dr.
Boleh.
Ni ikut
Boleh.
waktu ni, Dr. Sharifah.
Saya try, saya nak test share screen, saya boleh tak?
Boleh.
Nampak? Is it you can see my screen ke? Bukan saya nak.
Nampak screen.
Nampak screen tapi bukan slide you.
Nampak tak slide? Slide apa nampak kan? Okay kan?
Okay, nampak dia gerak.
Okay.
So what we'll do is, once we start at 10, I'll do some introduction first.
Okay.
Maybe for 10 minutes and then I'll pass it to you.
Yeah. Okay. Saya nampak Dr. Hazwan ada.
Ada. Dr. Hazwan, cakap hi.
Lama tak nampak.
Assalamualaikum. Dr. Asrul, saya ada sini.
Orang buat center, kami center tak ramai. Center printable electronics ni baru dan tak ramai lah. Jadi ni lah salah seorangnya ni lah Dr. Azwan.
Kena. Sekarang Dr. Azwan attest dekat UM tapi you punya office dia dekat yang dekat apa tu? Yang kat apa itu kan apa?
Dekat saya ada office dekat Maida.
Dekat apa? Dekat Maida kan?
Ya betul.
Sama dengan ni lah siapa?
Dengan Aida.
Dengan Pak Aida.
Ya.
So macam mana sekarang ni apa? Lab okey ke? Boleh sekarang ni UM still can access lab lah untuk postgrad?
Dah sebulan dekat 2 bulan saya rasa ni sejak diberi bagi izin mengikut ni kan mengikut SOP kami dah ada lah rasanya bulan kedua dah ni.
Kita still yang ni case I punya kita orang PG boleh tapi still follow SOP lah. Lab macam 3 orang. Bobo ni the last case lah. I punya student kena positif pula. Slow pula.
Research lain tu. Okey, boleh kita mula ke Dr. Sharifah?
Boleh.
Okay.
Assalamualaikum and salam sejahtera. Good morning to everyone. I see we have not just from UM, I see we have from UniKL, Dr. Azmida, we've got UKM, Dr. Jaharia, and I'm sorry if I've missed any others. So thank you again for joining us. Okay, so good morning everyone. My name is Sharifah. I am your MC for today's lecture. So we are very honored to have one of a prominent researcher in the area of printable and flexible electronics in Malaysia, Dr. Asrul Nizam bin Abdul Manaf. For your kind information as well, this lecture is co-organized by the HFPE EDS together with us at the Center of Printable Electronics. So before we begin, there are a few housekeeping announcements. We would like to kindly remind everyone to please ensure your microphones are muted if you are not speaking to avoid any disruptions throughout the talk. If you have any questions for the speaker, just type it in the chat box or you can ask your questions at the end of the talk. Okay, we thank you for your cooperation. Right, before I call Dr. Asrul to the stage, I wish to take just 10 minutes, okay, just 10 minutes of your time to give an introduction of CPE and also an introduction of the IEEE EDS. All right, I hope you can see my slide. Can you see my slide?
Yeah.
Okay, thank you. So just very quickly, Center of Printable Electronics CPE was established in 2017, but we are fully operational only in 2019. Only started in 2019. It's being led by Professor IR Dr. Nohayati Soin as its director. We've quite got a lean members. We only have 7 personnel. We've got 1 postdoctoral visitor, Dr. Hanim from UITM. We've got 1 postdoctoral research associate, which is Dr. Hazwan, which is also linked with CRES and MIDA, right? And we've got 2 support staff. We've got Hafiz and Puan Hidayah. Thank you again for this. Without Puan Hidayah and without Encik Hafiz, it's hard to move actually. So thank you for you all. And we've got 2 full-time students. I see now we've got Azwa here. Azwa is our PhD student. She's inside this meeting as well. Thank you, Azwa, for coming. So the objective of this talk, of our CPE, is basically we look into innovative solution for wearable healthcare application. So we look into healthcare, but slowly we are also moving into other branches as well. We are exploring agriculture and PPE. And these are our key research focuses. We are looking into sensors, electronics, RF, which is the electronics interfacing with the sensor. We're looking at energy harvesting, looking at solar cells, as well as materials and processes. So we've got some current projects, and these are our equipments. If you are interested to collaborate with us, please do email us at cope@um.edu.my. If you are interested in using our facilities, yes, you can also email us. So next, I want to do some overview for the IEEE EDS. So EDS is it promotes electronic devices for the betterment of the humanity, and it fosters professional growth of our members. So these are the field of interest within EDS. So if you feel that you are within the studies of research, yes, please do become a member of IEEE EDS. So it's not at all expensive. It's just $20 and USD $20 per year, which is less than 100 ringgit, and students can receive even more discounted price, which is about 10 USD. So these are the benefits of joining IEEE EDS. You can get free access to the webinars, technical contents for the top IEEE journals. You can network with all the EDS members. We can help you to network with other international IEEE members. You can get access to cash awards, recognition. For instance, we have the student fellowship programs. You can get fundings for not just research, technical research, but also for humanitarian projects and many more. So these are the EDS publications, okay, that EDS sponsor. We are within Region 10, R10, which is here. Okay, there are in total 220 chapters in IEEE EDS, and we are the only one in Malaysia. This is a picture of the members in IEEE EDS. I think this was taken before COVID. We've got some prominent lecturers inside IEEE EDS. We've got Prof. Naushad from Uni10, we've got Prof. Zahirul from IIUM, we've got Prof. Nahayati, we've got Prof. Suzy from UKM. This is our current chair, Dr. Sabirin from UITM. We also hold a lot of numerous lecture series and DL programs. For instance, in August, we did DL Distinguished Lecture programs with Professor De Souza from Sheffield University and Professor Rais Zadeh from the US. We also are known for our Let's Talk series, okay, where in this is kind of like a forum. It's quite interesting. The attractive thing about it is that we invite industry speakers as well, not just academic speakers, and we talk about different topics every month, different topics within the electronic devices scope every month. So yes, please join us. This is quite open. It's open to public. We also are very active in our humanity activities. For instance, we did some donation drive for COVID, and then we also developed some face shields for the students. And I think just recently we did a ceramah kesederhan, the awareness talk, I think last week. We are also quite active in our STEM activities. This is being led by Dr. Aliza and Dr. Azwin from IIUM. So this is a good thing about being in the IEEE. You are also exposed with other You also meet with other people from outside your own universities. So yeah, these are the activities that we did. And only recently, only just last Saturday, Dr. Azwin and Dr. Aliza did a training with the students to use Raspberry Pi. So these are pictures again taken before COVID. We are quite recognized by other IEEE chapters. We are being awarded with the Outstanding Chapter in 2018 and 2017, and these are some of our awards. We are also co-organized some conferences only last 2 years back in 2020 and 2021. We did a virtual conference. Hopefully in 2022, we can do a hybrid conference in Langkawi. So that's ICSE. So I hope you guys can, everyone can send some your current work, to our upcoming conference. We also acknowledge women in the engineering. So we did, this was done in March, earlier this year. We did a forum to talk about the women's in engineering. So this is our SOCMED. So yeah, you can visit us at Facebook, YouTube, and Instagram to see our activities. Again, please do join us at IEEE EDS. We welcome your participation so that we can collaborate and join our activities. So, right, let's dive into the talk. So Dr. Azrul, while you are sharing your PowerPoint presentation, you can share it now.
Okay.
So while Dr. Azrul is sharing his screen, I'd like to give a brief biodata of our speaker today. So Dr. Azrul Nizam Abdul Manaf received his BE and ME degrees in Electrical and Electronics Engineering from Toyohashi University of Technology in Japan in 2001 and 2005 respectively, and PhD degree in Engineering from the Department of Applied Physics, School of Fundamental Science and Technology at Keio University, Japan in 2009. He was an electrical engineer with Toyo Memory Technologies in Berhad, Malaysia. Since 2009, he has been with USM as a senior lecturer, and he was promoted to an associate professor in 2015. He has authored and co-authored more than 60 international technical journal or conference papers. He was a recipient of several innovation awards at national and international invention competition. He currently has 2 patent filings for DNA sensor and CMOS-based tunable inductor. His current research interest includes development of microfluidic-based DNA sensor integrated with CMOS circuitry, miniaturized of fluidic-based inclination sensor, bio-inspired-based microfluidic acoustic, pressure and flow sensor for underwater system, microfluidic-based memristor, microfluidic-based tunable inductor, microfluidic thermoelectric generator-based energy harvesting, graphene-based transistor, and micro 3D fabrication. So since 2016, he has been an academic staff with the Collaborative Microelectronic Design Excellence Center, CDEC, in USM. So the floor is yours, Dr. Azrul.
Assalamualaikum and very good morning to all the participants, and then first I would like thanks to chairperson for a kindly introductions, and also thanks to the centers of the Printable Electronics, Universiti Malaya, and also the IEEE EDS, and then for these invitations. Okay, so today I will share with all of you what our current research specific on the printable electronics that we already started in since 2017, the 2017 or the 2016. So today I will focus on the lab on flexible stretchable circuitry board for wearable medical applications. So before I start, let's give me about 5 minutes to introduce our centers and my research group. So that what our current topic or the current research that did in my group. So like explained by a chairpersons, so I'm from University Science Malaysia, and then I belong to Collaborative Microelectronic Design Excellence Center. That is one of the center of excellence under Senate University Science Malaysia. So our center we established on the 10 November 2005, and then that under MOF, the Ministry of Finance, and then started operate in the 2007 under University Science Malaysia. So currently we have 70 staff. So we have the 4 academic staff and 7 research officers and the 4 assistant engineers and 2 admin staff. And then currently we have 15 postgraduate students that be supervised by 4 academic staff at CDEX. So our location is at a main island at Penang. So if you have been in Penang, we just located at Bukit Jambul. So if you have been stay in the Equatorial Hotel, so it's just about 5 minutes walking from Equatorial Hotel, and then from the airport Penang about 15 minutes from the airport. So that is our office. So before that, our center at the engineering campus, and then 2013, so we moved to the Bukit Jambul. So that we at the new USM campus, we call as a sign at USM. So in terms of the industrial linkages, we also, I think the Prof. Hayati already familiar with us, and also Prof. Dr. Jaharia from UKM also. That we also have the MPW program, the multi-program wafer, so that we offer services, that means to all universities and then SME companies, so to access our EDA tools that are available in our servers, that can do a tap out at the Silterra through a multi-program wafer program. So recently, we have signed NDA with TSMC and also the ST Micro. So that for tap out for the chip fabrications. Right. So if you have a chance came to Penang, please visit us and at our campus at top hill at the hill. So that sea view. So that as a sign at USM campus. Okay, so let I focus on my group. So actually, my group, so we are focused on the integrated circuit and sensor system. So what our focus in my group? So we are focused on the 2 areas. First, on the sensor development, and also on the silicon-based CMOS circuitry. So that when we have a sensors, so that we be able to integrate with a CMOS, but it's not towards to the monolithic chip, we towards to the heterogeneous integrations. So that's why for a sensors, so we apply 2 technologies. First, as a printable technologies. The second is the silicon micro machining technologies. So, but today we more focus how our research, that means our activity, the research activities, how we implement the printable technologies, and then how we do the sensors development. So currently in our group, we only focus on the 4 type of the sensing mechanisms. So we focus on the electrochemical based sensing mechanisms and FET based sensing mechanism, the acoustic and the maps, only the 4 types of a sensing principle we focus, and then we develop the sensor based on the 4 types of the sensing principle using printable technologies that we are focused on the flexible and stretchable substrate. So then when we develop the sensors, so that we do the monolith, not we do as a hybrid integration. I call as a hybrid integration because we don't have the facility to have the monolithic chip integration. So actually the circuit we fabricate separately using the CMOS or the silicon process, so that we do the hybrid integration on our printed circuit board. So that like the FR4, and also we have explore on the TPU and also the polyvinyl alcohol, and then to develop the sensor. So this is one of the examples that done in my group. So we have the EC sensors, then we do the modification on the electrode. So this one fabricated in our lab. So we fabricate the circuit. That means we have the microcontrollers, and then we have the temperature sensors. That this substrate is a TPU. It's a Teflon polyurethane. So mean this substrate not only bendable but can stretchable. That's why I will talk later how we do the optimization as a circuit trace if we want to apply it to on the stretchable substrate. So this one of the that of course. So we integrate with the microfluidic that towards to any specific applications that you using the PDMS, the polydimethylsiloxane. So this is what the roughly about my group. So that we focus on the sensors, and my team we have the others academic. So we have two more academics. So where they are focused on the CMOS circuitry. So like the ADC, DAC, and also the power amplifier, PMUIC. So towards to by combining the sensors and that circuit, we develop what we call as the IoT physical device. So the one a system for the system on chip lah. So but it's a hybrid integrations. So today I really appreciate to the Prof. Nohayati group, and that to invite us and to invite me to share what our current activity that I in a specific area on the printable electronics, then how I apply on those type of the sensors. So this is what I want to touch today. So the printable, stretchable electronic devices, but specific on the medical applications. So this is what the outline for today. So I will explain the motivation how we focus on the lab on printed circuit board. Some I use in term lab on the printed flexible. I use some I use the lab on the FH, the F, the P, the flexible, the FPCB, right? So the lab on flexible printed circuit board. So that, but today I just give some idea in our group how we focus on the develop the a few sensors, PS using the electrochemical sensing, using a printable electronic, how we develop the PS sensors, and also the strain sensors that with a specific application for like for a wound monitoring. And then how I will give you some as how we explore in terms of the substrate selection, how we do the selection, the criteria into the printing technique. A lot of the printing technique that available in the current technology, we have the inkjet base, we have the screen printed base, and then we have a lot of few type, but they have the criteria that you have to match with start of your application and your ink condition. That how we explore by a collaboration with the School of Material Sciences, Prof. Malaya, and also the Prof. Zulkifli from USM, how they how their group that develop for us the stretchable conductive ink, because our group we only focus on sensors. We not expert in the chemistry and the ink formulations. That's why this project, this printable, we work with the chemistry, and also with the some we also purchase from the overseas the ink. Alright, so that one we have the ink, so we just do the sensor design and do proceed on the fabrication based on our design requirement. So and then we just we touch a little bit some outcome, some output in work on the stretchable conductive ink with the Prof. Zulkifli from the School of Material Sciences, and also Prof. Al Mariati from School of Material Sciences, that we apply in our strain sensors, right? And then the last before I end, so I will explain some work that how we apply to prove the workable printed circuit board, not on the FR4. So if you're so all of you familiar with the printed circuit board, but mainly for the FR4, the flammable retardant 4. But if you are going to design a circuit on the stretchable substrate, mean you have the it's not rigid substrate. So that means a few criteria that you have to consider. So that I will give some examples, and then how we did in my group. So that we out with the summaries of my talk. Okay, so I think Prof. Nohayati, and I think all of you already familiar with some they call as the lab on chip, right? The lab on chip mean how they are towards to the diagnosis, right? Towards to have to simplify the diagnosis system, and then in 1890 when the MEMS technology, the microelectronic mechanism, the MEMS technology is explored in the 1980. A lot of sensors is come out. I mean the small pressure sensors that will be able to have the more the micro valve. So this is a type of the advancements of a semiconductors fabrication, so that they have the lab on chip. So that means how they have technologies, how be able to miniaturize the functions of the lab on one substrate. But in our group, because we try to make it what is the affordable technologies. I mean, what is the simple technology? Because if you rely on the lab on chip, we need go to a lot of complex of fabrication tools, such as like the sputtering, the evaporation. Of course, you have to have a good lithography. That means based on to miniature. That means for a pattern fabrication. So that's why in our group we still using a term lab, but we rephrase not lab on chip, but the lab on printed circuit board. But we try to explore the various type of the printed circuit board, from the FR4, the flammable retardant 4 substrate. There is a normal rigid substrate that the common use in any circuit board. But we also explore in the new subset that towards to not only bendable but also can be stretchable, right? So mean on that board, so we can have sensing the functioning. So mean we can have the microfluidic to flow the samples, and that they come to the reaction chamber or any sensing region, and then to make the detection. And that we heterogeneously integration with our silicon interface circuit, and then to do the amplifications. So by having that technologies, that we can minimize, because by integrate the flexible and with a channel, so that means we can minimize the volume of the sample of volume can minimize. So when the volume can reduce, so that we can make it the system can be a fast detection. That what, and also when the volume is reduced, mean we also can reduce the waste to the environment. So that the motivations of the development for the lab on printed circuit board. Right. So towards to that technologies, what we focus in my group recently, we are focused about the smart bandage. So how we can develop a smart bandage system, right? So what the problem with a current smart bandage? So the current wound management. So when you have injury, when you have a wound, they may have a injury, for example, like the diabetes patients. So after they done surgery, that mean they have have a wound. That mean you have to, the doctor have monitor the wound condition. That means you have to clean the wound, and that so after. But the current bandage, right? So when they attach on your wound, so the doctor cannot get objectively data in the real time. So normally, so doctor will advise you, okay, please come to the next week and then to hospital, and then they will open up and they can see, oh, I mean they have to do a cleaning again and then do some antibiotic treatment, and then they will paste again your wound. Based on some literature review, when they have to the doctor will replace a new bandage, right? So like I have a case like in my mother, the last 5 years, they have an injury on the L4 and 5, and then they have a treatment. That means the operation. So every week have to come to the clinic, to the hospital, and then to replace a new that bandage. One bandage is cost about 100 something, 150 ringgit something. So that for about 3 months. That means they have to do the monitoring. So but some papers, so we did some review. So when the doctor is open up the bandage, they also can affect, they call as the second injury. The second injury to the wound. That's why they will affect your prolonged wound, right? Your that because the lacking of the objectively measured data in the real time. So that's why from this motivation, with how we can able to do some a new evolution of bandage, but not only a bandage, but be able to give the objectively a data or not that wound condition is still okay. That means no need to change the bandage, right? So for example, we need the objectively a data on the wound condition, right? So from that, so that we can have the closed loop system. So we do some literature. We did some literature review in our group. So that is that we found a good papers from the Matthew is Brown. That this group published in a frontier in bioengineering and biotechnologies. So from that paper, we found so that mean they have a few parameters that we consider your wound condition. So mean the pH condition at the wound area, and the oxygen level at a wound condition, and also the temperatures. And also some data, they also have a strain analysis of the tissue, right? So from that data, so maybe it's a possibility by using the printable technologies, how we be able to develop the pH sensors, so that we can know, so this what is the conditions of their wound. So this is a normal scale, right? So that is what the pH, that is from their study. So that is the range of the pH. So if your pH, the wound pH is more alkalic, so it's easier to the bacteria to grow. That how to reduce back a healthy pH. So they need we give this a proper the amount of dose antibiotic. From that paper, some they are what a system can give a right amount of the antibiotic. That means to do a treatment to what that is to work to what we call as a precision medicine. So mean the precision, so mean we can have the right using a correct data, mean the objectively a data, so that we can know what the amount of the dose like the antibiotic can deliver to the wound, so that can be a precise control of the wound condition. Right? So there is a few the parameters, but in our group we still not focus on that oxygen level yet. So we focus on the pH sensors development and also the temperature sensors development. That means it's that towards to that applications. So when we go through a few so that means so we know that is our design specification for our pH. So this is our the resolutions of our temperature sensors. So by knowing that what the design spec, that means the parameter, what we call is a sensing parameters. So that how we going to develop the sensor. Of course, must be using a right bandage as our substrate, right? So that the second thing, so it means towards to that, what is the material that available? That means for a pH. So because my group, we are the electrochemical sensing principle. That the focus in our group. That's why how we using the electrochemical sensing principles to act, that means to develop the pH sensors using the three working electrodes technique. So that we go through a few they did some paper from Hardy et al. They studied variations of the sensing materials for a pH and also the pH, the range of pH and also the sensitivity. So then because that we find one, and then the second, why you want to handle with any the bio, that mean this the pH must direct attached to the skin, that means to the wound. So it means you have to ensure the biocompatibility of the material, right? So that's why, so we have the G, and then we find the GO that, but the good that is going from the next equation. So it should be, that is the good, that if 57 is most a good sensitivity. So that means we can see it's the range from 4 to 9 at least. So that means we can see that GO can go to 4 to 10, and then but the sensitivity is still lower compared to the others. So that's why also that how we can apply the GO and then do some ink formulation on the graphene oxide as a sensing membrane for the pH sensors. So that some there we start to that a study on the sensors development and also the design specification towards to that, like the wound monitoring applications. So from that, and then now we come to how to do the selections of the materials. That means the substrate itself, because we try to make it okay. Hopefully one day attached to the skin. How to make it to avoid the inconvenience to the patients. So that we go through some the paper from the Rogers et al. That's a very top that we consider as the founder of the Printable Electronics group. So they did a good study in terms of the conformal conditions, right? So there is some the substrate thickness, right? So that means if you see these diagrams, you also can have a detail on that paper. Sciences is published 2011. So that is the thickness. If your substrate thickness is 400 micrometers, is 400 micrometers, and then you can see they still have a gap. So how the analogy of 400 micrometer is such as like our silicon wafer thickness. So if the current silicon wafer thickness is about the 400 to 700 micrometers, so that the roughly the thickness of wafer. mean that the skin, the image of the skin structures, and then you can see that it still have a gap. It's not really adapt the good attachment on the skin. So this a group, they going to study in 100 micrometer, and then you can see they have the improvement, but still have a gap. They cannot follow the conformal structure of the skin, so of the body skin. And then they towards to the 36 micrometers, and then they did improvement, but after they reduced to 5 micrometer thickness, and they can see a very good conformal on the skin structures lah. So but right now the latest is the latest thickness that did by the group from from Yamaguchi universities. They presented 1 micrometer thickness. The 1 micrometer thickness substrate. On top of that, so they have the array of the OTFT, the transistors, the array of transistors. So this is 2011. So that's why. And then the other criteria, so if you have to more sensitive, and then you can make it a good conformance on your skin, the other criteria for the selection substrate, not only the flexible, not only the stretchable, but also the thickness of the substrate, right? So that is, but this need some a good chemistry lah, the good chemist or any the material expert, how they did a study, they mean in terms of the substrate for mission, right? So this is the second. So what during that our group, so that we mean that we know. So in that that one of the criteria is some the thickness. So it's some I think that is a famous picture. So if you did some printable electronics, so that they have some that is a normal pictures that we capture, we take, and then we put in our slide as our that we call as the trend, the innovations in the printable electronics. And then is some from that continue from this part, and then what the other issue. So what the other issue that studied by the Prof. Somaya, this is from the Prof. Somaya group at the Tokyo University. They also considered as a good as a founders and good researchers in the printable electronics. So this is our the silicon rubber, and then there is a paraline 1 micrometer. So their group actually I will not explain detail on that material. So they have a nanomesh conductors. This is a gold electrode. So they do the evaporations that electrode on the polyvinyl alcohol. So the polyvinyl alcohol we consider as a water soluble materials, right? So they printed the pattern of gold electrode on the PVA, and then they use water. I mean the heat treatment. So the PVA we remove. So when the PVA is removed, so the pattern straight away can be attached on your skin. So what they are studied there, so if the other technique, so mean the issue on the skin effect. So mean this area, so it's a fully attached. So that means they not any like the air gap for the skin to breathe. That what they are mentioned in that paper. So by having that nanomesh electrode, so they have the gap. So the skin to breathe, they naturally breathe. So that can be effect the effect of the skin. So that's why in the group they come out a new material that the substrate they call is a polyvinyl alcohol. So the polyvinyl alcohol, there is a water soluble material. So that when you can print it first on that, and then you can put on your skin, and then can use a heat treatment or the water spray. So that PVA we remove, only the pattern can be attached on the body. So that also in my group. So based on a few literature review, so in our group we did a few substrate. So we using a few substrate to develop the sensors such as like the polyvinyl alcohol, and then the TPU, of course, the PET and the polyamide, and also the latest we also some did on the gelatin as subset. And then you can see there is a data. So by having the nano mass electrodes, so it mean they no inflammation, right? So I mean they no inflammations is compared to the other subset like the silicon and paraline, right? So so this is a few the thickness lah, a few subset that available in our group. So by do the design specification, the sensing parameters, and then that we have to consider also the substrate thickness. So based on the application, the second, I mean how we can do the printing. That mean the make it our substrate can be a flexible. So all can be a stretchable. Right. So this a few some study done a very top research group. And so of course from the Illinois, from the Tokyo University, the post-America. So these a few the evaluations of the evaluations of the transistor and the evaluation of the printable electronic stretchable devices. So if you go through, actually we have a three type. That means the three method to make it our subset, to make it our flexible devices. So I just quick. So the first they call as a deterministic composite. What mean deterministic composite? Mean we need the substrate. We have the substrate. On top of the substrate, we deposit with the thin film, but we make it the thin film like the thin film make it like the geometrical. Like if you're familiar with a Japan like concept of origami paper, so that mean they have a pattern like a pattern like origami, the geometrical. So that's why when you stress that, so the origami we also the stress lah. So that can be the concept, but you need the fabrication tools. I mean to do the pattern, the patterning to form the like this image. So the structures. So that mean when when you stress, so the spring. I mean the geometrical structure will be stressed. So that one of the method. The second method they call as a random composite. What is a random composite? Because why you want to have the stretchable, right? So I mean you want to develop the sensor. It mean must be conductive, right? But of course, when you talk about the conductive, a metal is a conductive, but metal is not polymer, because one is not have a polymer, they cannot stretch. But the polymer is an insulator, it's not conductive, right? That's why one of the methods, I mean, they do some ink formulation, some composite formulation. That means by advancement in the gold nanoparticles, the silver nanoparticles, and then they do the mixing. I mean, we have to ink, how the ink formulation, we using the PDMS like a polymer or the PPS pedal, but we can mix with the conductive particle, but must to ensure the homogeneous mixing, so that can be have the conductive polymer. So that can, when you stress, it also can be conduct the electricity, right? So and then the third technique they call as the liquid metal, the intrinsically stretchable. So what there is some uniqueness. I mean, we need to have the micro channels that we insert the liquid metal in the micro channels lah. So that means so the fluid movement we consider the stretchability, right? So but in our group, so we focus on the second technique. So that's why we explore on the printable technologies, how we have worked with the group from the chemistry school of the material expert, how they can help us to do the ink formulation, but the conductive polymer ink formulation, but can have a highly conductivity. So as a baseline to a copper thread, the copper like similar to the the PCB that commonly used in our printed circuit board. But of course, to have a similar 10 power 6 like the PCB is a really difficult. So we try at least 10 power 4. That is a sufficient lah, based on application. If you want to do the antenna or any the inductive, it must have a highly conductive materials, the highly conductive ink. Right? So that so by select the random composite too, of course we need to have a few printing technique that available lah. So that means we have the inkjet printing technique and the eject dispense like the concept of 3D printing, right? So that means they have each printer, of course, they have a different type of the ink character. The most important is the ink viscosity, right? So if you use the inkjet, the viscosity is too light compared to the screen printing. Screen printing, that we need like a paste, like the ink is like a paste, like a conductive paste. So you have to match with your type of a printer, and then you have to match with the properties of your ink. That's why if you buy if you are purchased from the overseas the ink, and then you have to ensure the properties must be matched with your type inkjet. So there is a few viscosity that you have to consider. Basically, like it cannot be a paste. That is can be a so they cannot. That mean the nozzle cannot operate properly. So if you use the screen printed, so it means the ink must be like a paste conditions, right? So in our group, so in my group, so generally we have a two type of the printers that we focus on the inkjet, and then we also have the screen printing. I mean to start the explorations in our printable electronics. So why with the inkjet? Inkjet, if you compare to the screen, the inkjet, if you can minimize the ink, that means you can avoid the waste, but the very challenge lah. So from our experience, I work with a few group from the ink formulation. It's very challenged to do the ink formulation for the inkjet based printing, right, compared to the screen printing. And then the second, so you have to consider also the cure temperatures, because when you buy the printer, they have a spec on the heater. That means the cure temperature. So I mean the ink that you buy must be at the range of the printer cure lah. So it means so if your ink, the cure temperature is too slow, so that can avoid that can reduce the pattern resolutions, right? So I mean how we mesh the printing, the printing type must be matched with the type of the ink. So how we choose the ink criteria, ink viscosity, of course the line width, the line thickness, and also the uniformity. Normally when the ink come out, that means they will start to cure from a center to the edge. The center to the edge. Some that mean they have some uniformity between the center and between the edge lah, right? So that's why if you see the inkjet that the thickness, because this is the inkjet base, so that is the thickness is 0.1 to 1 micrometer thickness, but the screen printing the thickness is too thick, right? That's why based on your applications, so that you have to choose the right printing, then based on your sensors and your device application. So this good preview done by Takos Meyer. So they did a preview but specific on the TFT, the thin film transistors, right? So in our group, so that's what we are focused. So now we are going to develop the heater, the micro heater, so mean the temperature sensors and also the pH sensors, but the oscillation we use what the available in the market, the commercial sensors. So the concept is, so when they detect the temperature is highest, or the heater will heat up or the heater heat up, so that can be a localized temperature. So that we use the flexible wires and then connect to the MCU, the microcontroller. You need to do the processing. So today, the today talk, I just focus on few printable for the PAs and using the electrochemical sensor. So that's what we the whole system that we imaging the dream, the illustrations of for the good the smart bandage. So mean when they detect the conditions, the wound is a bad or the alkalic, so mean they need have the storage of amount of the antibiotic can deliver the localized deliver to the wound condition, so that can be make it your wound can be a fast healing, right? And then, so why they need the oxygen? Because from there I studied, so the oxygen is needed. That means to ensure the cell have a sufficient nutrient. That means to healing. That means to heal, to do the healing process. So through that, so mean we have to do the selection of the substrate, and then you have to do the selections of the printer must match with the conditions, and also the thickness substrate also be in the considerations before you proceed on the any application for the medical devices. So this some our work a few, I think the last 3 years in 2017, right? So that we work with the one of the Jabil. So that what they are going to we want to have the conductive polymer. That means the conductive ink, but not only conductive, and also not only bendable, but stretchable. So if you're familiar with any the PCB fabrication, we have the polyamide, but the polyamide they can only flexible, but only can flexible, can bendable, but cannot stretchable, right? So if my experience, so if you have a one layer, if you have the 4 layer, 6 layer, at the end the flexible be a rigid, right? So that is some limitation. Of course, the thickness main the most important concern if you want to maintain as a stretchable and the flexible devices. So now how we do develop, and then for example, like your substrate is a flexible, but your ink is a metal ink. You use the silver ink. The silver ink is a more common and established ink that you can available with the cheaper cost lah. The silver ink, but the silver ink they're not flexible, they're not stretchable. So mean when you are printed, when you are printed the silver ink on the stretchable substrate, so when you stress, so the ink will appear off because they have a compress and tensioning problem between the substrate and the thin film. So mean if you are going to apply for the stretchable application, so the ink also must be able to stretch without having a peel off problem. So from that, so we at that time, so we did some study because we using the PDMS is a polymer, because my group familiar with the PDM because we started earlier the PDM in our microfluidic that we buy the PDM we bought from the signature. So that the company, so that, but it's a polymer, mean it's a insulator, it's not conductive. so that time, so they do some study on mixing lah, on the mixing with a silver nanoparticles with the ink, and then they do the homogeneous mixing. So this some cross-sectional view, the SM image, so we can say that have that's a the green color is a filler. So that means the silver nano particles, but you can see they have a gap. So when they have a gap, so that can reduce the conduct activity. And then, so that means there has a large gap between the flake and between the particles and the other particles. So I mean, if we can reduce the gap, so I mean you can improve in terms of the conductivity. So that is some at that time. So they do some mix how to reduce the gap. So that some change the silver nanoparticles using the silver flake, the silver flake, and then that can minimize the particle to the particle contact that do the development is the stretchable conductive ink using on the polymer. So this at that time 2017. So there is some they use the strengths, so that they do that the PDMS, so that the ink there's a mixing between the PDMS in the silver nano but the silver flake. So that means they good in terms of if you flake also mean the intensity is the same. So that means it's a good conductive. And then the others work, so that we also have this is with a Prof Marati group. So that we did, so this the strain sensors. So how to make it the sensitive, how to make it a very sensitive strain. So that we so the same, so that we using the PDMS. So the PDMS that we mix we do the play around with the ratio of the silver nanoparticles, right? So this is some so this is my one of our PhD students. So that work the collaboration with the School of Material, so that they so she already graduated this year and also back to Myanmar, right? So that is so we do some so at that time, so by assist by the from the School of Material Pragmatic Group, so that they do a lot of the ink formulation lah. The ink formulation depend on the percentage. So there's a nanowire, so they with a few PDMS, so that that is some if with the eco flat, so that can be as a capacity more than insulators. So there is there's a mix between the PDMS. So actually that is the ratio. So we change from the 0.1, 0.15, 0.2, 0.2, and then 0.25, 0.25, and then 0.3. So that is the percentage of loading, the filler loading, right? To get hard, I mean to do the in term to improve the conductivity. So by having that factors, so actually we did some good the gauge factors, and the strength the strength range can be up to 70%, at 70%. But the latest the strength, I mean the stretchability, I think the last week we had one keynote talk from the Prof Malaya is go to 1000 percentage stretchability. It's a very good. So we only a 70%. So that is some the of course you need to play around lah with the material properties. So this is what we tested. Then we do some the twisting analysis, see how the robustness of the ink, and then that we also did some hysteresis studies. And then there is some studies on we put on our finger, and then we can see how they're sensitive to check the finger. That means to detect the finger motion, right? So that is and then the others. So we also do some the fabrications and that technique that we of course towards to smart bandage. So that we bought that bandage from pharmacist. So this that we do a printed on the CNT ink. So that is some our first test. I mean the test on the conduct activities, and also we also some tested this just play around. That means we tested also on the gelatin. Then we want to see how the addition between the ink and the restart of the substrate. Right. So that we also develop the PS sensors. So we publish on the sensors material, but we still suffer in terms of the sensitivity. So this is still ongoing to that on the formulation, the ink formulations. And then the others in our group also, we are trying to make it like the water-based ink, mean to for a biocompatible process. So that is that the others we have the carbon black. So we do the printing on the carbon black. So the sensors that from the ink. So that is a printable technologies. So that is we printed at our laboratories. And also that the my group also we also have some exploration on the FET devices for the any sensors application. Right? If they want the crash gland, so that we do some salmonella detection. So we that our own the telemet, our own custom made printed the own custom made on the electrochemical sensors. So we prove the formulations. I mean gold, and then next we do the RGO. But we've done a first tester on the PCB that we going to replace a few substrate lah. That means to do the salmonella detection using the electrochemical sensor. So that we design, that is our own design for EC sensors. So and then the same we also do a tested on the others work. So in our group, because we also do a testing on the heavy metals using the PCB, the printed circuit board, that we can have do some take some the data on the on the heavy metal detection, and then we reach the LOD until to 32 part per billion. So this is some the integrations with microfluidic now still in ongoing with my PhD students, that we try to make it the flexible, the stretchable. So that on the microfluidic integrations. So this our lab. So that's one of the examples. So that is the screen printing base. So that is that we bought from the Volterra, and then we also do a few tested on the multiple subsets. So like I give so at the so, and then that is our the board factory. So that is for the inject base. So the inject base, so that is that we are printed on the TPU. So this is a TPU subset. So we attach the TPU on our rigid subset. So after we done the fabrication, and then we peel off that TPU from the platform. That means from the rigid platform. And then the others work, we also have studied the possibility. That means to develop a circuit trace for a printed circuit board. So this is a normal the Gerber file. Is if you do the design on the printed circuit board, the rigid FR4, and then you can see here, if your design on the PCB, that means that is a normal. That means they have the sub edge corner. That can be the sub edge corner. That can be the sub edge corner. So that can be the sub edge corner. But when you apply on the stretchable, mean your subset will be stretched. So mean they have the possibility this sub will be break, right? So from that, what we do some work with a school of mechanical, and then they do some stress analysis. So that from the stress analysis, we can see, so with a sub-edge, so that more stress, that easier to break. That's why we work with ongoing, how we can have the standard fabrication. That means the standard fabrication, like if you design the IC, we have the PDK file, the process design kit file. So the same. So if we apply on the stretchable, so we need to study how the curving, right? So that is what we design the conventional PCB the gable file, but we need to have a curving. Also the same for the pad. And the pad also, that we cannot have like the sub-edge corner. That's why we have a design with because we so that we have the pad also there. So like this, they have the curve. So that we do some study what we call as the PDK file, the process design kit technology for the stretchable design, for the circuit design. So this our tested. So we can see here. So this the PDMS. So that is the server ink. So that we have the LED to turn on, and can see that the power is supplied. So this is the microcontroller, the MCU, and then to control the temperature monitoring. So that we can see here. So when I attach the head, when we attach with the finger here, then we can see the changes of the temperatures lah, right? But of course they have the ambient temperatures. That means they have not a right in. So that means we need so the reading is done, and then the MCU can work properly. The MCU can flow the current rating about 16 milliampere. So this is what we prove the surface mounted, the SMT. On the with a small component, with a larger component, and then with a medium size of the component to prove for the stretchable flex, the stretchable printed circuit board, right? So that before that, actually, to get that outcome, a lot of, so because the second problem, when you did with the printed circuit board, that means the SMT, of course we need the paste, that means the conductive paste, right? So the conductive paste also must be the stretchable conductive paste. So if you have a rigid paste, that your like we have a needle, that means we have a pin, the foot pin of your MCU. So we use stress, so the paste also will be open up. So that means your component will be peel off, right? That a few we go through lah. So the challenge. So this is what we did for the stretchable. So the flexible circuitry on the temperature sensors. This one of that from Jabil. So that they come on the World Trade Journal on 2016. The flexible the printed circuit board. So this is what I will do some printing. So that is on the PVA. So this is on the polyimide. So that is on our bandage. So this is on the gelatin. So that the bandage we bought from the pharmacy. So made it pure transparent. And then, but we still suffer to have a good, the very thin film of the substrate. So that is the PVA. So that's on the TPU, the Teflon polyurethane. So as summary, so we done some implementations of the printed technologies to develop the pH sensors and also the strain sensors, and then we tested with the stretchable conductive ink, and also we do some proof study on the development, the process design kit for the printed stretchable the stretchable printed circuit board. That means that for with a surface mounted the SMT. Then next we are going to have the microfluidics technologies on top of the few sensors to work to the medical applications. So this is the announcement from my group. So that from our collaborators and also from our group and then all the student staff and also some application for this work. Thank you.
Thank you. Thank you, Dr. Asrul. Thank you, Dr. Asrul, for the very engaging talk. You have shared with us not only your active research at USM, but you had also given us a comprehensive overview of current published work by others. So providing us some insights, some ideas on what we can do for printable research. So thank you, Dr. Asrul, for that. So now I open for questions. So if you have any questions, you can type into the chat box or you can open your mic and ask directly. Here I've got in the chat box, I've got 3 questions.
Yeah.
Here Dr. Liana asking, what is the minimum line size that this 3D printer can print?
Okay, for in our case, because I use inkjet and the print screen, the minimum 600 micrometer.
600.
Yeah, 600 micrometer right now. That what we do the optimize. So it means the gap also not less than 600 micrometer. So if we design a few technique, a few pattern is less than 600. If less than 600 micrometer, have the overlap because that based on what our lab, what our available printed in my lab lah. So that we only can do 600 micrometer line.
Okay.
Yeah. Because we still difficulties because the optimizations of the heating, the cure temperatures. The problem is what are different between us and the others like the top guy. I mean like the Tokyo Universiti. They create their own printer, their own ink. So it means their ink already optimized with their fabricated printer. In our case, we buy the printer. We buy the printer and then we buy the ink. So that a lot of the mismatch lah between the ink formulation and also the printer. So that the case like there is a normal if you buy the Epson printer and then you only can buy the Epson ink, right? That is a if you have a Epson printer, you cannot buy the ink from brothers. But in the current printable electronics, in my group, because we don't have the expertise to build the printer, so we also buy the printer from the outsource, I mean from the overseas. But we also have so say some ink. For example, some printer, some company they only have a few ink limitation. That means like so. But if you want to tailor in your sensors design, you need have the uniqueness of your ink, right? Your unique ink. That's why this difficulties lah. That means to do the mismatch between the printer and the ink formulation. But if you go through is the papers from that Somaya they done. So there is some their ink that is inject say 30 to 50 micrometer line width can go. But of course, if you have a right ink that optimal with the right printers, if they inject, so that the line width that you can go. So like a skin print, that is like the maximum that can go. But must have ensure right viscosity, right cure temperatures that with your printer that you available in your lab lah. So but the inject that the resolution lah.
Okay. Next question. From your experience, which substrate and type of ink should we best avoid due to poor adhesion or brittleness? What type?
Krypton.
Krypton.
Krypton. The substrate is a really difficult about the additions. So that's why in my lab we focus on the TPU and also the PVA. The easiest substrate is a polyimide. That's already established. The polyimide you can do any the attachment with a copper and also with a silver. The most established ink is a silver ink. It's most established ink. That can easier. So that's why we also in my lab we also open the services. If anyone to do a printing, but we offer for a silver. But for the carbon, like in our business, we have a carbon ink. We have the stretchable conductive ink. We not offer to services. That's only in a research mode. But the silver is already established lah.
Okay. And then for your smart bandage, you directly printed on the cotton bandage, is that right?
Yeah.
So any specific issues you face when printing on textile?
Of course. The first about the connectivity.
Connectivity,
Yeah, the connectivity, because when you have a cotton, that's why when we do the printing, that's why we cannot. The good is with a single layer should have the connectivity. No, we need multiple layer. Here with the one layer, but one layer still have a first, and they not now. That's why some that cases we do about the 20 layer.
Okay.
To do the painting, so that can be the more connected. That others the filter. That's why. So if the single layer can be enough conductive, that a good lah, because that you can lower down your cost and you simplify the process. But in our experience, so that we need the multiple layers to have a good conductivity. Yeah.
Okay. Okay, from Miss Azwa. Thank you, Doctor, for your talk. You mentioned earlier that ink formulation of inkjet printer is difficult compared to screen printer.
Yeah.
Can you share a bit? What are the challenges?
Okay. So that just from my I just say what we facing the problem lah, right? So let I see some. So that our okay. So that the inkjet. So that the inkjet based printer. Of course, the inkjet based printer, the really the critical is the viscosity. Mean you cannot do a paste, right? And then they have a nozzles. And then the problem is, so when you want to have but if you want to just print silver, fine, should be no problem. But if you want to tailor-make your ink to be a polymer, but must be conductive. When you have a polymer, but must be conductive, you have to add with a particles, the silver flake. Because from that, we have to tailor-make in terms of the nozzles, because they can have a clot, the nozzle. That the first we facing. So a lot when we pay off when we in the cartridge. So actually how we did in my lab. So actually we bought a lot of the free cartridge, and in this cartridge they have a span. So we have to learn how the mechanism of the cartridge span. So the first when we they need a high volume mass of the ink. So because the span, so in this cartridge they have a span. So when you fill in the liquid, so some liquid the span we absorb a few of liquid, right? So they have to right calculation between the volume of cartridge and the how your ink can absorb to that span lah. So it means the cartridge is too complex is compared to the screen print. The screen print is easier because you need to have a mesh. You just design a mesh and then you just screen print. But the problem is the screen print compared to inkjet, the screen print you can waste the ink. but here you can minimize the volume, but the cartridge is too complex in terms of the spun component that you have to write volume of the amount of the ink. If not, that your ink will be dry, right? And then the second, the size of nozzle must be considered with your particle size. That means your silver particle size, right? And then also the viscosity and also the heater, the cure, because the inkjet, the ink is too it's not viscous, it's not too viscosity. That's why if your cure is too slow, so that can be merged with others. So there are a few some we have a facing problem lah about the cartridge cloth, and then about the optimization of the cure temperatures, and also that they avoid us about the print resolutions. Yeah.
Okay, thank you, Dr. Astro. If CPE has any problems, I hope you can ask you to help. You have a very extensive experience in this. Okay, last question. If you have someone asking whether you have a position for postdoc.
Postdoc. Actually, we just end the postdoc application. The last the deadline already finished, and then the new postdoc will come on the October lah. So right now we don't have any vacancy yet lah for a postdoc. Already fulfilled with 2 postdoc lah in my groups. Yep.
I see. If you do have position, do you do advertising? How do you advertise your? Maybe some people want.
Yeah. Actually, we do the advertise on our Facebook for a CDEC, or for our center of Facebook, and also our website lah, for call for the postdoc. The last submission is on the on the June, and then that means the result already done lah, by the last on the September, and then the new postdoc we start to register on the October. Yeah.
Okay, so if people who interested to join Dr. Ashok, please look at the FB, the social media.
Our social media for my centers on the social media on our centers, and also some on our website lah. Yeah.
Okay, so I'll stop the program now. But before that, I would like to present Dr. Asrul a certificate of appreciation. There's another question. Sorry.
Yeah.
One more question. Last one. Maximum which concentration can be used in case of RGO?
Mean the concentrations, we in our lab we not tested with the RGO, we use GO. So the GO that the letter that we did with my student is the 10 micrometers, that the micromolar. So that what we did lah. So that of course we have studied also the RGO. So the problem is the RGO. So we still study on the they need like to reduce GO from that our partner lah, that mean collaborator, they need some the toxicity. That's why some they study how using the acid absorbate, something like that. That can be all the water soluble RGO lah for ink. So is it you mean the concentrations of RGO or the viscosity of the RGO, or the concentration of the RGO that we use in our sensors?
I believe so. question. Okay, thank you, Ahmad.
Yeah.
Okay. So before I would like to before I end, I'd like to share. The Astro, can you unshare your screen?
Yeah.
Yes. So, sorry. So thank you, Dr. Ashwa. This is a CJ penghargaan appreciation from us.
Thank you. Yeah.
Thank you for your time.
Yeah.
For the lecture.
Thank
And
you.
we will share this sorry everyone. We will share the recording of the session in HFPE YouTube channel.
Okay.
If you to look back at the lecture, we will post it there.
Yeah.
Okay.
Oh, I see Prof.
Prof. Burhan.
Bonadim,
Yeah,
our Sifu here.
Yes, our Sifu. Everyone's Sifu is here. Yeah. Prof. Burhan is here. So before we finish, can I take a picture? If everyone can open their camera.
Yep.
So I can take a picture. Anyone? Yes, thank you. Okay, thank you. Anyone else? Okay. Yeah. We'll wait for everyone to open the camera. Okay, so all right. Okay, so I think I'll take a picture now. Okay. Even I didn't take. Sorry. All right. Okay. Thank you. Thank you everyone for coming.
Yeah. Thank you for
thanks Dr. Asrul.
Thank you for invitation.
Thanks Dr. Asrul Nizam.
Thank you.
Okay, thank you also to Prof. Burhan, my Sifu, Prof. Burhan. So I've started my MEMS, my MEMS research since 2001 with Professor Burhanuddin from Aiman. So Sifu of Aiman, and I was one of the graduate PhD students, first batch from Aiman. Prof, thank you very much. So now I'm leading the Center of Printable of Electronics. I'm still new, baby, not even I think 5 years. So thank you for all participants for the great talk done by Dr. Asrul Nizam. So of course later we will be having again the collaborative research. So we have to support.
Before I continue my PhD in Japan to 2006, actually I met Prof.
Dr. Asrul Nizam, insyaAllah.
At the IMANS. So he advised me about the microfluidic lah. At that time, I think at 2005. 2005. At the IMANS, That continue my PhD lah.
Yes. Yes, Prof. Burhan is everyone's Sifu, not just yours. Okay. Okay, thank you everyone. Okay, thank you for coming. Okay, bye.
Thank you, bye. Stay safe, take care, bye.
Bye.
Thank you, bye.